Hello everyone, this is Stas and welcome to my new TouchDesigner tutorial. And this tutorial would be about the interaction between particles and sign distance functions, or raymarching. We're gonna create today something like this one, where here is a raymarched object and here is an instanced particles, and you could stick it to the surface or make them float around somewhere. And the particles is driven by coral noise. And I started to dig this technique, this interaction stuff very recently, but I already discovered the many application and many uses of it. So for example, here it's about the same, but with physics. So particles is just bouncing from a raymarched object, and here's a particles creating a trails on SDF. The issue with this tutorial is how to make it simple for you, especially if you're not familiar with raymarched. As you probably know, I'm a big fan of raymarching, and I did 3 parts tutorial about raymarching in TouchDesigner, but I couldn't ask you to watch all 5 hours of it. What you need today, what you need to know for today is probably just some bits from the first part about geometry. And if you already more or less familiar with raymarching, you don't need to watch it because I explained everything you need to know for you. And these 2 components would be provided in description, and these more advanced examples. Well, it's not more advanced, it's just a different use of the same technique. It would be available for my Patreon supporters. So, as I said, we're gonna create this, but we would start from, not from scratch, but from this starting point. And as you could see, here we have particles, and we have raymarched, but they don't interact they don't interact. It's only calculated the depth, so they render it fine. So the particle that behind the geometry is hidden, but they just fly through geometry. While we need, they don't fly through. So this starting point, you could from this point follow this tutorial with me, and we would code everything. And to explain how it's created, this part here is actually a coral noise compute shader. It's you could find in the great tutorial from Bruno Imbrisi called TouchDesigner Coral Noise. It's 25 minutes and you could follow it. It's super nice tutorial, and I don't want to show you the same stuff and also talk a lot of time about it, so you just start from this. As you could see, I have about the same setup. So it's just feedback position, feedback velocity. The code is absolutely the same. Well, yeah, probably it's absolutely the same. Maybe I just rename some variables, I'm not sure. And the other difference is that Bruno used these boxes, this rectangle stuff, as the particles, while I'm using the spheres because it looks nicer and it's easier to calculate the distance in a way. Actually, it's not a sphere, it's it's just a point and the point sprite that's faking the look of a sphere, but overall you could use the sphere or a box or anything else here. It doesn't matter. And here I have a raymarched, just a typical raymarching, which also use the depth, render depth from my compute shaders to hide the parts of a geometry that would be covered by particles. And I showed similar setup in my raymarching part 2 somewhere about how to combine the polygonal rendering and raymarched rendering. But here I'm using a little bit more advanced version of it with a matrix, camera projection matrix, and big thank to Alexei Karpik and Tim Gerritsen to show this trick in the Discord, in the TouchDesigner Discord server, and I leave a link to their discussion here, so you could read and understand a bit more about how to use the camera matrix to calculate the position of a raymarched geometry. And the good news is that now you could use any type of TouchDesigner standard camera, including the arcball camera, which I'm a big fan of arcball camera because you could rotate, you could pan, and you could do everything, and it's nice. So, before we start, by the way, in this tutorial it would be a lot of references to different articles and other tutorials, so you could dive much deeper if you want. So, as I said, I'm a big fan of raymarching, and recently I saw this video about how raymarched and particles interacting in VVVV program. I don't know how to program in this VVVV, and I also found about the same stuff in Houdini and tutorial how to use raymarched and SDF function for particles in Houdini, and then I saw this similar stuff in WebGL, and this nice article about it. So I decided to do something similar in TouchDesigner. And here we are. We have our computing coral noise particles, and we have our raymarching, and we need to combine it somehow. So let's dig into raymarching. All we need in this for this tutorial, for this approach, is mostly the geometry setup and the normals. Let's talk first about geometry. Again, if you're not familiar with raymarching, I really advise you to watch first the raymarching part 1. But overall, the idea is that we could create the geometry not in polygonal way, but in, let's say, mathematical way. The easiest way to show you is to explain to you is to draw the SDF and raymarching for the sphere or to the circle, because there is not a big difference between two-dimensional and three-dimensional stuff here. So let's say we want to describe the circle in this sine distance function. What sine distance function is some kind of a function that would tell for any of our points the distance to geometry. And let's say we have, and in all in this type of geometry, we by default it's started in a 0, 0, 0 position, so in the start of coordinates. And let's say we have a sphere or a circle in a 0 point, and the radius of a circle is r, and we want to know the distance from our point P to the surface of this circle. How could we calculate it? Well, all we need to know is we need to calculate this distance. We need to calculate this length, and we need to subtract from it this radius. So the overall is the length of this point P minus radius r. And for the three-dimensional sphere, the formula would be the same. And why it's called sine distance function is because if our point P located here, for example, when we do the same formula, so for example this radius equals 1 and this length equals 0.5, then we would have the length 0.5 minus 1 equals minus 0.5. So if we outside our geometry, we get a positive distance, and if we inside, we got a negative distance. And for the sphere or for the circle, it's super simple. For more complex geometry, it could be much harder. But thankfully for us, Inigo class and other nice mathematicians and coders have already do a lot of work. So here, for example, formulas, functions for sphere, box, and many other geometries. And if you want to dig a little bit deeper, I recommend you to watch the Inigo class tutorial about where he explained how to mathematically calculate and why and how it works, the calculation for this capsule. But overall, you don't need to understand these formulas. All you need to know is to combine that and to use it. And if you become really good at this, you could create a pretty complex geometry like this head, which is consists made by T.D. Hooper, and the code for the head started here, and it's almost 400 lines. So sometimes the raymarched or SDF geometry could be a little bit painful to describe. So, but you could do it, hopefully. All right. And here I have geometry for this object, like a repetition of rounded boxes and a sphere in the center, but maybe it's a little bit complex, so we could do just a sphere, for example. As you could see, it's the same formula. Is a sphere equals length. Length is a special GLSL function that says the distance from 0 coordinates to the point P minus the radius. In our case, is 2. So if we, instead of all that stuff, if we return just a sphere, here is our sphere. All right. Now, somehow we need to get all of these functions be available for our compute shaders. So the particles know the distance to the surface of an object. And we couldn't just tell the one shader to look inside the other shader, unfortunately. So what we could do is to create a text dot. Let's make it syntax GLSL, It's not necessary, it's just good for syntax highlighting. And let's make a new and call is SDF. So we could store our SDF function here, and then we could reference to this file, to this operator, both from our raymarching and to compute a shader. So in the end, we would have the similar geometry, absolutely the similar geometry in both cases. The other approach would be to just copy paste this sense setup to compute shader here. But in that case, you would need, every time you change something in geometry, you would need to change in this geometry as well. So it's not very convenient, and I prefer to do it differently. So let's just cut it from here and paste it here, F, and when we save, let me just do it like this. Yeah, and where is it? And if I save this code, now we have an error because undefined variable and blah blah blah. So we need to include this file, include SDF, and now everything works again. So what's going on right now? The code from this part of code, from this new, is referenced here. So in a way it's copy paste here as well. And another thing we would need in our setup is normals. So we could do the same for the normals, but here is the problem, the issue with it. With normals, oh, by the way, let me explain how normals works, because it also would be helpful to you. Yeah, maybe I'll... Oops. No, all right, that's okay. That's okay or not. Yeah, okay. Let's do some more complex geometry, something like this. And you could imagine this is some kind of 3D geometry. And again, as I said, there is no big difference between two-dimensional and three-dimensional signed disk functions. So let's say we have a point here. In a standard raymarched setup, the normals is used for calculating the light, because if a light source is here, we need the normals of a surface to understand how much this surface should be lit, and the same for ambient occlusion and the same for shadows, and how to calculate the normals. We took 2 points here in the code. We took well, here we have in all 3 dimension, but here in this type we would have a 2 dimension, and we subtract and add a very small amount, the minimal distance here, and our minimal distance is just 0.001. So we took this point in horizontal, minus and plus, and we took these 2 points. It's also a super small distance, and we calculate the distance to the surface in all of these 4 points, or in 6 points for 3D geometry. And by knowing these distances, so the smallest distance probably in this point would be here, it would be here, it would be, I don't know, here probably, and yeah, something like this. So as you could see, the distance is very different from the distance of this point, and by evaluating this stuff, you could calculate the normal in this point would be facing somewhere over here. And it's the same for 3D geometry. And what we want to do in our setup, so let's go about idea. Here we have particles just floating around. What we want to do is, for example, here is our particle. Let's make it blue because we have a blue particles. And we want to change its velocity based on its position relative to the surface of a geometry. So what we could do is to calculate the distance, the closest distance to the closest point in the surface, like this distance. And also we could calculate the normal for this point, because in a way we don't need to, it's not necessary for the point to be on the surface. We could calculate the same manner the normals here. We could take this 4 points and get the shortest, probably, I don't know, it would be somewhere over here. Well, no, not not here, but probably. Well, anyway, it's we calculate the shortest distance to, well, it's also not the shortest, but I hope you get the idea. We calculate the normal for the surface in this point, and the normal would be again about the same. And now we could use this normal as a force. And again, it's not it doesn't matter, is it a particle inside or outside, or it could be anywhere. Our particle, we could calculate normal, and by calculating normal we now know the direction between this point, this our particle position, and the closest point of a surface. And we also know the distance. Yeah, this drawing become really messy. So again, we know a distance, and we know a normal. And we could use it somehow in our velocity. So, for example, we could send, if our point is here, we could just, with some force, we could send this particle velocity here. And this force could be somehow multiplied by distance. So if our point is very, very far away, it would have a bigger velocity towards the surface. And if it's somewhere nearby, the velocity would be much smaller. And we could have also the other force that comes from inside. So we could have two separate forces, because, for example, in the most cases, at least I think in the most cases, what we want is that particle wouldn't go inside geometry, but fly somewhere outside. So we have some like a small force towards geometry, but a super huge force that doesn't allow particles to go inside it. So let's implement all of this. Yeah, where I stopped. Yeah. So we could copy paste the estimate normal code here. The same for as a SEN, as a SDF formula. But on the other hand, then we wouldn't it wouldn't be possible to use the uniforms from GLSL operator here, because these uniforms it's like connected to this operator, and this operator it's not a GLSL, it's just a text that it doesn't have any uniform, so you couldn't type some uniform here. You could pass it, or you could send some uniform from here to here, but you couldn't reference uniforms from here. So this way we could either copy paste this estimate normal here but change zoom in distance to something different, or the other way, we could copy paste this estimate normal and paste it here in our, this is code for our compute shader. So now we have a code for normal, and we also need to include the same SDF as well, and include SDF. And I also know that we would need a new uniform, vec3, and we call it force. So we would have 3 values for it. The first value would be the shift, because the distance function tells us the distance to the surface itself. But if we have a particle here, we don't want our particles would be rendered here. We would prefer to have it not here. We would prefer to have it on a surface. So we need to subtract some small amount, the radius of a particle from a distance. And this shift value we would store here. It would be our shift value. This would be our, let me just, so x would be shift, y would be internal force, so it's a force that comes from inside and doesn't allow to move a particle inside geometry. And the third would be external force. So now let's go here. Let's go here to the calculation, because we don't need to do anything with the position. It's again, if you don't understand all of this code before, it's all taken from Bruno Imbrisi tutorial here. So I really recommend to watch it to understand what's going on with coral noise and how the position and velocity and the life and the noise factor, how it's affected the particles. All we need to change is the velocity, because right now the velocity is just aiding this coral noise, but we want the velocity be somehow affected with the force. So let's start coding already, because we need to start code. So let's call it force. Vec3 force, and let's make it 0. So we start with we start with 0 force. Now for making some effects for our force, we need to know the distance and the normals. So for a distance, it's a float, it's a single number, let's call it distance. Let's call it distance. I forgot how it's called. Oh, it's called sin SDF. It's sin SDF of our position, and our position is called the position. SDF of a position. SDF of a position minus this tiny shift, minus u force x. Alright, now we have our distance, and we also need to calculate the normals. Oops, vec 3, let's call it normals, equals, our function is called estimate normal, also for the position. Yeah, we don't need to subtract here anything. And now let's create this logic that I described in this drawing. If our distance is less than 0, so in other hand, if our distance is negative, is somewhere inside our geometry. If our distance is less than 0, then the force is minus normals multiplied by our internal force, so it's u force y, and also, as I explained here, the distance also should have effect, so and multiplied by distance, so let's call it is push from force from inside, and else force should be the normal. We could copy paste it. But we just change the amount of a force from outside. The only stuff maybe not so clear is why it's minus, because our normals is of course facing from geometry, and while we need our particles go to geometry, so this is why it's negative. So we calculated the force, and now the same as here, we in the coral noise we multiplied by delta. This is a super small amount, depends on our frame rate, because our frame rate should have effect. Since our velocity is feedbacked back to the position, then the frame rate should have effect on the amount of velocity. So velocity plus the force multiplied by u delta. and we left everything else. So let's hope everything will be fine. No, it's not fine. Something needs. You mean this? Oh, yeah. Because here we have u minus minimal distance and we don't have this variable. We could just say the float u mean distance equals 0.001. It's also good to have it the separate estimate normal here and the other one inside, so we could have the different minimal distance, because sometimes for example, if I make it like this, this distance is also affecting the overall look of our raymarched geometry. So maybe we would like to change it in raymarching, but we don't want to change it in compute shaders. So that's why I didn't include the estimate normal here, because I could do it, but rather I did it here. So let's save. Everything works fine. Now let me press reset, and now we have our. Is everything alright? Yeah, it seems so. At least it doesn't go, our particles doesn't go inside geometry. Let me turn on the display and let's work a little bit with the force. So first of all, let's put the internal force very much, like 50. Oops, we have a lot of velocity damping. Let's make it smaller. And let's also decrease any life changes, so the particles wouldn't burn and wouldn't die. Okay, here are our particles, and they shifted to, if I put the 50 here, to have a lot of force coming from the both directions. So if we have a lot of force from here, okay, if we have a lot of force coming from here and a lot of force coming from here, then our particles, most of the cases, would be curling and noising more or less on the surface. And this is what's going on here. Let's also make it per period of noise a little bit bigger. But why it's not on the surface? Because our shift value is too big. If we make it 0, again we have a lot of velocity. So what I'm looking at, as you could see, this is why we need our shifting, and it should be, right now I do it manually, but if you stick with the sphere, you should probably calculate it from the radius of a sphere. But for the box, and especially if you use some box like this, it would be much more difficult to find a nice value to shifting. But right now, something like 0.5 looks fine. So if our internal force equals to 0, then our particles could go inside our geometry. And this is not what we want. Here, our particles goes inside. So that's why we have a big force coming from the inside. But from the outside, maybe we would like to have a much tinier force, like 0.5. And now our particles is somewhere nearby this geometry, but not not stick to the surface, or maybe it should be even less. Yeah. Well, not so much. And we could play with the period as well. So right now it's just playing with the parameters. Overall, we did everything we wanted, and it's time to explain some details and some hints and hacks and tools. So why I did it like this? Because now I can insert here a switch, and I can switch between different geometry. Let's make some super simple geometry, like just a sphere. Yeah, something like super simple geometry. Sphere with a radius equal 3. And now I could switch into other input, and we have the different raymarching. Okay, that's it for the main part of the tutorial. I hope you like it and I hope you understand it. If not, please leave a comment and I'll try to explain in more details. Oh, one more thing. I'm not sure, have you seen it or not? But I've seen it. Some particles is flickering here, and this flickering is happened because, or maybe if I increase the amount of particles, it would be more visible. Wow, yeah, that's nice. And there is some flickering over here and over there. It's going on because sometimes the position for two different spheres is they are on the same position, and if the two spheres on the same position, the Z-buffer fighting could occur. And what is Z-buffer fighting is when two geometry of a different colors trying to be rendered, and since we have two different colors, it could some glitchy flickering, blah blah blah. And the simplest solution with it is to add a little bit of noise, just a super little bit of noise, like non-monochrome of 0 and amplitude 0.001. Well, I still see some flickering, maybe 0.5. Yeah, now it's better. And by the way, of course, you could insert the different operators and different stuff here. Also, what you could do is, let me switch back to more complex geometry. Sometimes you may want to sometimes you may want to change the shift, because sometimes it's nice to see our geometry outside. And by the way, by changing the velocity damping, you have an effect how it's here is a little bit jumpy. If I set to 99, it would be much more jumping, and if I set to 0.5, it would be much less jumpy. Okay, so now we have a shifted particles that's around but not on the surface. Maybe you would like to do it. So but it's not only for the kernel noise. You could add here, instead of kernel noise and instead of this logic with two forces, you could implement something totally different. For example, here in my example for the Patreon supporters, I have this example. Here's a raymarched geometry, and the particles is bounced from it. And how it's bounced, it's just a dot product between the normal of a surface and the velocity, as far as I remember. The other way, the other idea you could do, for example, let me try to do it super quickly. Maybe I'll succeed in it, maybe not. So for example, I could say if distance less than 0.1, some small amount, then velocity multiplied by 0. And what it would do, it would stop particle on the surface. At least in my idea, it should stop particle on the surface. Let me try to increase a little bit of velocity. Yeah. So, and now the when the particles is too close to the surface, it just sticks on the surface. So sticky geometry. And you could come up with something really different. And it's also the sequence of the order how you do it. So here the first I add the core noise to the velocity, then I add a force to the velocity, and then I check if it's too close. And if I change it like this, it would be a totally different stuff. So the orders is matter. Order matters. And yeah, so you need to think how you would like to calculate your velocity, in which order. All right. And about this one, it's also available for my Patreon supporters. And what's going on here is probably you've seen my old tutorial about the particle trails, or even better, the again tutorial about making the particle trails. And here it is. We calculate in the position. The difference here is that our position is stored in 1 pixel width. So also I changed the dispatch size to have it in one row. And then with a feedback loop, the trails is calculated, and it's rendered here. And in this setup, I don't even need to render raymarched itself. So sometimes you don't need to render it. And if you wouldn't render it, it's also here I made, by the way, I used this face by TD Hooper I showed you before. I closed already. Anyway, I used this face SDF function, and I reference it the same matter as we did before, but in this setup, since I didn't render the raymarching stuff itself, I don't need to do it. I could include all SDF inside this code, so it would be more convenient. And another stuff I wanted to show you is with this example. Here I have geroid parameters, so it's parameters for this geometry. And this is a little bit tricky, because as I mentioned when I talk about normals, you couldn't reference these parameters here in SDF. So how it's made? Here for my SDF and for my normals, by the way, here I used normals here inside this code. I also asked as an input geroid parameters. And then I changed the geometry based on these geroid parameters. So when I, in both in the compute shader and in raymarching, calculating the scene, I also need to pass not only the position, but also I need to pass geroid parameters that comes from here. And it's also binded here, so I'm using a bind here. This way the geroids are the same and the parameters are the same for the both compute shader and raymarched. So probably that's it, and thank you for watching this rather a little bit tricky and a little bit maybe confusing tutorial, because so much reference to the different tutorials and different articles, but I hope you understand how to deal with it. And I remind you that you could download the file with these two components and experiment it with yourself and do something. And please, if you experiment with different forces and come up with an interesting result, please share it, because I would like to see what else is possible with this kind of technique. And I'm also gonna continue and work with it, and probably someday the part 2 of this tutorial would be out as well, because probably there is much more ideas and much more forces could be applied to the same stuff. And that's it for today. Thank you for watching, and goodbye.